then Sn assumes each of the three values infinitely often. And Sn is usually gamma usually appears, and if Sn is not gamma, then its two neighbors are gamma. So gamma is a steady state, so to speak. And these indices of irregular shifts, where you get the gamma minus 1, gamma plus 1, they can be partitioned into k subsets where k is some integer, each of which satisfies a linear recurrence. We also proved that conjecture 1 implies conjecture 2. This was also proved by Xinyu Sun, a student of Doron, with additional results. And Doron and Sun proved the two conjectures of mine for m equals 3 and j between 1 and 10. So the first pile is at most 10, and since 10 is already halfway to infinity, so Doron proved it almost integer. And here you just see, sort of look at the column Sn, this is the shift sequence. So after a while it just has these two values, 8 and 9, 7, 8 and 9. And so you see here these, so 8 is a steady state, and then you sometimes have 7 and sometimes you have 9. And they appear more sparsely, but they go out to infinity. They will never disappear. And so there is a certain fractal-like pattern in those. And so you can just observe some of these pictures, what's going on here. So you see that little perturbation of the three numbers are excluded from the union. Three integers are excluded from the set of integers already causes all this fractal-like behavior, which is sort of amazing. Okay, so we have that. So here are some questions. What determines the number k of irregular shift sequences Sn? We don't know. And probably Echad can find out, Echad Shalosh. Shalosh Echad, sorry. For some perturbation sets X, we get gamma n is equal to n for all n without getting these n minus 1 and n plus 1. But we don't know when this happens. And then we can ask about such perturbation for general BT sequences, not just those particular ones, this tau. And actually we have for some infinite class we do know, but in general we don't. And the same question can be asked for S-fold complementarity and fraction complementarity. I didn't yet say what these things are, but I'll explain at least one of them. So as I said, Doron and Xinyu Sun, is he here? No. They proved the two conjectures for three files. And they wrote this: the method discussed here should be extendable to prove the conjectures for Wythoff's game with more than sweeps. A numerical method instead of the symbolic one presented here may also be developed to improve the performance. I'm sure that Echad will soon do that. And then they continue: we hope the result presented here would be a stepping stone for others to finally prove the conjectures, and better yet, to provide a constructive polynomial time winning strategy for the game. And so that reminds me that there are two reasons why the, well, let me go. So, S-fold complementarity. Let S be some positive integer, and what does it mean what do we mean by S-fold complementarity? Simply that every positive integer covers exactly S times. So S equals 1 was the case we discussed before. And for the case S equals 1, there is also, you can ask about that the intersection is empty, but when S is bigger than 1, this doesn't happen. So there is a theorem of Kevin O'Brien and Larsson, over Larsson, that it's almost the same condition that we had before. Alpha is irrational, 1 over alpha plus 1 over beta is equal to S. Before we had 1, now we have S. We say that alpha is less than beta. And A is a sequence of all the n alpha integer part, and B is the same as beta. Then the sets A, B, S split the positive integers. In other words, the union is S times the integers. Each integer is covered exactly S times. So O'Brien proved that by his generating functions and power series, and here are some fans of that who are addicted to those kind of proofs. Larsson proved it purely combinatorial, and I simply observed that the beautiful pleasure proof that I gave before just carries through for this case also. And so you're left with the K, there was this K there, which is covered, and so K is recovered S times, so it just goes through.
So how many papers about these books?
The paper of O'Brien appeared in the Journal of Number Theory, but he has other stuff there. I don't remember how many pages devoted to that. Larsson has a purely combinatorial proof. He just, I think today he submits the paper. He has a final form of the paper to be submitted to Richard Novakovsky. It will appear in the proceedings of one of those Doros game meetings. And that's pretty short, but it's not. And he includes an appendix by Aviezri Fraenkel where this nice proof appears. So he has this appendix. Yes. So now here's a theorem of Uspensky and Gram. So Uspensky proved it by using some heavy machinery. A theorem on simultaneous Diophantine approximation due to Fraenkel, and Gram gave a nice purely combinatorial proof. So here is the theorem. If alpha 1, alpha m are positive real numbers, and suppose that n alpha 1 up to n alpha m split the positive integers. So the union is all the integers, and pairwise they don't intersect. And it turns out that m is at most 2. In other words, we cannot have more than 2 such sequences. So, of course, this is the homogeneous case. What do I mean homogeneous? That there is n alpha 1 up to n alpha n. There is no n alpha I plus gamma I. This would be the non-homogeneous case. For non-homogeneous, of course, you have such splitting. Take the evens and take the numbers congruent to 1 mod 4 and 3 mod 4. So you split in more than 2. Yeah. So here's another question. Does Uspensky and Gram's result hold also for S-fold complementarity? And we just, Peter Hegarty and Urban Larsson and me conjecture that the answer is positive, except in some trivial cases which I don't want to explain here. And I think we have almost proved that, but almost isn't good enough. Now I want to tell you about some, as it says here, a conjecture. It has been solved completely for the integers, and